Hello, and welcome to lecture number 2 in our series out of chapter 2 here. This one focuses on the periodic table. This is the fifth lecture in our overall series on General Chemistry 1. And so, as we're looking at the periodic table, now there's a lot of origin stories about the periodic table, but most of the decent ones, and most of the ones that actually are substantial, kind of focus around Dmitri Mendeleev. And the reason why Mendeleev is so well regarded in this area isn't because he's the first, isn't because he was so innovative, but because he kind of did it the best. So he wasn't the first to introduce the idea of periodic arrangement, of using the octave rule, where every eighth element was had shared properties. He wasn't the first to group together elements into groups based on properties. But what he was able to do was, by setting up the table in such a way, in his case by increasing atomic mass, what he was able to do was show that when they were arranged in order of increasing atomic mass, those other principles that were discussed also happened to become true. So you could look at breaking it up and finding that every eighth element ended up having common properties. And so how he arranged his table was by increasing atomic mass. Now, this proved to be a less accurate method than the method used in the modern periodic table. But to Mendeleev's credit, the proton had not been discovered yet. So he had that kind of going against him. But what he was able to do is he was able to arrange the elements into columns, and those columns were based upon the common chemical and physical properties that were shared by those elements, what would later become known as periodic properties. And the other thing that he did, and this is really why his table stuck, was he understood that in order to keep this periodic nature, there had to be gaps in his table. That is, places where an element should go, but doesn't belong there yet because it hasn't been discovered yet. And one of the most common cases, one of the kind of romanticized ones, was he knew that based on his periodic table that there should have been a gap below silicon. And so he looks at the properties of silicon, he looks at the properties of carbon, he looks at the properties of tin, which have been discovered, and recognizes they all have common properties. There's a gap between the silicon and the tin in that particular column that needs to be addressed. And so he addresses it. He says, look, this compound is going to have this particular density. It's going to create this kind of a compound with hydrogen. It's going to have this kind of reactivity, this kind of density, this kind of boiling point. And sure enough, when that element, which he called ecosilicon, was discovered and given a new name, germanium, germanium had many of the properties that Mendeleev thought that it would. And his estimations for melting point, for boiling point, for reactivity were very close. Now, germanium is not the only example of that, but it's probably the most famous one because germanium was discovered relatively short order compared to Mendeleev's lifetime. But that was one of the reasons why Mendeleev gets a lot of credit for the periodic table and its origins. Now, moving on to the modern periodic table, we will see that many of the constructs that Mendeleev put into place are present there also. Key difference, elements are arranged in order of increasing atomic number instead of increasing atomic mass. If you look closely on the periodic table, what you'll see is that there are instances where the mass order is out of order. Just looking at this periodic table here, you can see that cobalt and nickel in period 4, the first row of transition metals, those are out of order. Nickel should be earlier if we follow Mendeleev's order instead of cobalt, but it is actually the reverse because cobalt has fewer protons. So minor little things like that represent one distinction between our periodic table and the Mendeleev periodic table. Now, a commonality, the elements in columns do have similar chemical and physical properties compared to those, the rest of the ones in the column. For the horizontal rows of the periodic table, we refer to those as periods. That is what gives the periodic table its periodic nature, is the fact that they are arranged in these rows, and that each group of columns, sometimes referred to as a family, is known to have similar kinds of physical and chemical properties. And each of those 18 columns has that in common. So even if I look at some of the transition metals, what we'll find is that a lot of the transition metals in a given column have similar kinds of properties, make similar kinds of compounds. Now, some of those columns do have group and family names. We'll talk about those in just a second. But what I want you to do, if you have access to a periodic table, if you have a paper copy somewhere around you, I would encourage you to get that out. And what we're going to do is draw on this periodic table to show off some of the common families, some of the common hotspots, known areas of the periodic table that will be useful to us in later practices. And so for those of you that are in my section and in my lecture class, this periodic table is going to be very useful to us. We will add to it as the semester goes on. If you're watching from another university outside in the world of YouTube, this is still a really good reference to have. And you may not be able to use it for all places and all situations, but it's a nice reference to have. So get out your periodic table, and we're going to do a couple of things. Now, this particular periodic table has a couple of attributes that I really like. You can see that on this particular table, they have shaded the nonmetals in blue, the nonmetals in blue, the metals in a tannish yellow kind of color, and the metalloids or semimetals in a green color. Now, not all tables do this. Some do, some don't. This particular one here that I'm showing you that the university gives out does not. So if you have one of those more blank periodic tables, what you're going to want to do is draw in a line for yourself that features where this divide is. And the divide that we are interested in is this staggered staircase line that I'm drawing in right now. This staggered staircase line is what divides the metals from the nonmetals on the periodic table. So metals are to the left-hand side, nonmetals are to the right-hand side. Now, you'll notice, based on this drawing, that some of the ones on that staircase itself are indeed metalloids. That is, substances that have metallic and non-metallic properties at the same time. They kind of fit in the middle. They may look metallic in some ways, but have non-metallic kinds of properties, and vice versa. Another thing that you want to do, if your periodic table does not have labels on it for the periods, And for the families, you'll want to go ahead and add those in. I would also add in for the families, this will become much more apparent as the semester rolls on, but you may want to put in what are known as the CAS numbering system. When we talk about chemical bonding in chapter 4, those numbers will become a lot more apparent and useful to us in determining how many electrons are available for bonding. So the CAS numbering system, which goes from 1A to 8A, tells us how many electrons are in the outermost energy level for a given element. Now, there is a CAS numbering system for the transition metals. It's a lot more complicated, and so we actually aren't really going to discuss it. It does give us some information that's useful, but it's not something that is really worth a lot of time and examination. A couple of other things that you can do, though. Big, broad families. So this big, broad family from scandium down to element number 112. This is known as the transition metals. And these metals have a variety of properties that are kind of interesting to us. Now, another big, broad property, big, broad group that we can look at, the lanthanides and actinides here are known as the inner transition metals. And that is because their placement, you can see, is actually in the interior of the periodic table. You can see that they actually belong right there between lanthanum and hafnium, between actinium and rutherfordium. And so their common names, the lanthanides, are for the first element in that group, the lanthanium, and the actinides for actinium number 89. Other common families. Let's start in group 1 here. In group 1, so from lithium down to francium, those are known as the alkali metals. Alkali metals are known most commonly for being highly reactive in the sense that they react with air and water. Right next to them, I'll do this in red. Right next to them are the alkaline earth metals. These are also reactive with air and water, but to a lesser degree. Both of these groups are common, and when they react with water, they will form bases as a result of those reactions. The other group, so That's the majority of the metallic groups that are worth studying and investigating more closely. On the other side of the table, we have over here in pink, these are your noble gases, sometimes referred to as inert gases. They are so called because they are extremely unreactive. And it's weird to use a word like extreme for something as benign sounding as unreactive. But what we have to understand is that this is a rarity. Most substances, most elements are quite reactive in some kind of a way, at least with something. For the noble gases, some of them outright will not react ever. They stay atomic. They don't even react with themselves. For others like xenon and krypton, we can react them with extremely reactive gases like fluorine, but the resulting products are so unstable that their use is relatively limited. In yellow here, we will mark our other prominent group of non-metal substances. These are the halogens, and they are the opposite. They are extremely reactive. So they are kind of like the non-metallic analogs of the alkali metals. And so actually what we'll find is that alkali metals and halogens often react very, very, very violently with each other and produce very, 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 very stable compounds when they do. So those are the primary groups of the periodic table. Let's now investigate a little bit more into kind of some of the things that make these elements unique and kind of special. So for metals, metals tend to be shiny. They tend to be solids. Really, the only exception to that is mercury, which is a liquid. They tend to be very good conductors of heat and electricity. They tend to be malleable, meaning that we can pound them into very, very thin sheets. They tend to be ductile, which means that we can draw them into very, very long, thin wires. And that malleability and that ductility, that flexibility that we find in metals is one of the reasons why they make very good building materials. It's also why we use them for a lot of different kinds of uses in our homes, be it ductwork, be it, copper wiring for electrical purposes, all of those things. They tend to be very resilient materials. Nonmetals, on the other hand, tend to either be solids that are very, very brittle and fragile. If you've ever encountered elemental sulfur, it's kind of a powdery crystal of sorts. You can get it in a crystalline form, but it doesn't take a whole lot to grind it down into kind of a powder. Bromine is the only example of a liquid in the nonmetal. So there are only two elements in total that are that are liquids in their natural state, mercury for the metals and bromine for the nonmetals. Most nonmetals are gases. Again, there are some solids in there. Most of them are powdery and brittle kinds of solids. The rest are usually gases. And those gases, those solids, those liquids, regardless of what phase they're in, they're non-conductors. So they lack the flexibility of metals. They lack the shininess of metals. They lack the conductivity of metals. And they tend to be in phases of matter that make them really not very good for anything in the same kind of way that metals are. In between the two are your metalloids. And what we see with metalloids often is that they contain both metallic and non-metallic properties. So for example, they might be shiny like a metal is, but relatively brittle. Silicon's a good example of this. Silicon has kind of a natural shininess to it, but when you start to try to manipulate it like a metal does, it just kind of falls apart. But what's good about metalloids is we can often use them, but they have semiconducting kinds of properties. So they tend to be lighter weight than metals are in some senses. And their semiconducting properties actually can allow them to do certain things that are kind of useful to us. Again, going back to silicon, we use silicon most commonly in computer systems for making microchips and processors and other things. So with all of this in mind, let's do a little bit of investigation. Let's identify some elements based upon these descriptions. So for example, this nonmetal from group 15 in period 3 is used in matches. Now, to answer this question, I'm going to have to go back to the periodic table. We're looking in group 15, period 3, and so we can see that where those two cross each other is in phosphorus, element number 15. So the answer to this one, question A, was phosphorus. Which is element P. This transition metal from group 4 and period 4 is used in aerospace due to its strong but lightweight alloys that it can form. It can also be used in medical implants. So again, we're looking for group 4, period 4. Go to our table. Group 4 is here, period 4 is here. They cross up at titanium. Element number 22, symbol Ti. This metalloid from period 3 is critical to the computer industry. Again, I've got to go back to the table. Period 3 only has one metalloid. Common mistake is a number of students will identify aluminum as a metalloid as well. It is not. Aluminum is considered to be a full-on metal. So the only metalloid in period 3 on that staggered staircase line is silicon. Now, there's one more thing, one more concept that we want to bring out with our discussion of the periodic table, and it is this idea of average atomic mass. Now, average atomic mass is what is on the periodic table if we look at the atomic masses on this table. So most periodic tables will include 2 or 3 pieces of information. They will include the atomic number, which is usually shown in the bottom right corner or bottom left corner in this case. There's the elemental symbol itself. And then most periodic tables will also include some sort of a decimal number. And that decimal number, which is not focusing very well on the camera here, but that decimal number is the average atomic mass for that given element. Now, how do we get those average atomic masses? Well, that comes from a weighted average. And so what we do is we take the weighted averages for all of the masses of all of the different isotopes for a given element. And we calculate that average atomic mass by multiplying that natural abundance for each isotope by its mass and atomic mass units, and then adding those all together. So if there are 5 isotopes of a particular element, we multiply the natural abundance multiplied by the mass for each of those 5 isotopes, and then we add the resulting products together. Now, a natural abundance is the proportion of a given isotope, usually given to us as a percentage, relative to all of the other isotopes. So, for example, carbon. Carbon has three well-known isotopes. Carbon 12, which makes up like 98.9% of the carbon. Carbon 13, which represents another 0.8%. And carbon 14, which represents the remainder. Almost all of the carbon is carbon 12. And we can see that represented on the periodic table, because if you look at the atomic mass of carbon, the average atomic mass of carbon, 12.01, indicates that the majority of the material is carbon 12. But those natural abundances are the percentage values. Now, we can use those average atomic masses not only to tell us the mass of a given atom, but we can also tell the mass of a given molecule just by simply adding together those individual masses for the individual elements in a given compound. And those names come out one of two ways. We can either call that a molecular mass, that is for something that is covalent in nature. It's the mass of one molecule. The example we give here is ammonia. Ammonia has one nitrogen atom and three hydrogen atoms. And so to find the molecular mass of ammonia, we take the atomic mass of nitrogen and we add it to 3 times the atomic mass of hydrogen to account for those 3 hydrogen atoms. We end up getting, in this case, 17.09 AMUs, atomic mass units per molecule. Now, if we're dealing with an ionic compound, technically the correct term for an ionic compound's unit is called a formula unit. It's not called a molecule technically because there are no individual molecules inside of an ionic compound. It's a crystal. There are lots of pieces that are all kind of interacting with each other in this positive, negative, interactive ionic attraction kind of sense. And so technically speaking, it is called a formula unit. However, it is just as common and just as meaningful. If you say molecular formula or molecular mass for an ionic compound, generally speaking, no one's really going to correct you on that, even though it is technically incorrect. So for calcium chloride, the formula unit for calcium chloride is CaCl2. There are 1 calcium ion for every 2 chlorine ions in calcium chloride. To find the formula mass, I would take the mass of 1 calcium atom, 40.08 AMUs, and add it to the mass of 2 chlorine atoms, 2 times 35.45, to get the total mass of the total formula mass of 118.98 AMUs per formula unit. Again, if you said it was 118.98 AMUs per molecule, technically that is incorrect, but you're not going to find too many people that are going to really call you on that. To close out today, let's go ahead and do some practice problems with calculating average masses. And so the process that I use is a little different from the one that is usually written in textbooks. What a textbook is going to tell you to do is it is going to tell you that you need to turn all of these into decimals, and then multiply the mass times the decimal to get the number. And do that for all of these. And then add them all together. Problem with that approach is that if you have abundances that are less than 1, or even less than 10 for that matter, moving that decimal the correct number of places, doing that in your head, often leads to more problems than it's worth. So I offer a slight modification of that. And the slight modification is this. We are going to multiply the percentages by the AMUs directly. Now, yes, this is going to give us numbers that are huge and gigantic and don't make a ton of sense. But we will correct for that at the end when we divide the end number by 100 to give us the actual atomic mass. So here we go with this. 19.9924 multiplied by 90.4838. Calculator gives you 1808.98823. Now, we still have to abide by our significant figure rules here, which means we cannot add extra digits just for the sake of extra digits. I've got 6 significant figures here. I've got 6 here. My answer needs to have 6 as well, which means that that last digit there is going to be that 8, and we're going to round that up because of the 8 next to it. So after properly rounding, 1808.99 is our correct value. We're going to do this again. 20.9940 multiplied by 0.2696 is going to give us, this time we have 6 sig figs in the AMUs, but only 4 in the percentage. So we're going to round to 4. That's going to give us 5.65, oops, excuse me, 660 AMUs. Now notice how I wrote it here. This is going to help us with the last step for significant figures where we're looking at decimal places. By keeping the decimal points lined up and the place markers lined up, I'm going to have a much easier time seeing how many significant figures, how many decimal places I need to round to. Last one here, I've got 6 sig figs in the AMU, 5 in the percentage. So I'm going to round to 5, 21.9914 multiplied by 9.2465. To 5 significant figures is 203.34 AMUs. So now I'm going to add these together, and we can see that the first and the last are both to 2 decimal places. The middle one's to 3. I'm going to round to that second decimal place when it comes time. 1808 plus 0.99 plus 5.660 plus 203.34 to 2 decimal places is 2017.99 AMUs. Now, if I stopped here, I would be saying that the atomic mass of neon is 2017.99. That number does not make sense. No atom has a molar mass greater than 200 something. So I know I'm in the wrong, but if I divide by 100 and move that decimal place over 2 spots, I get 20.1799 AMUs. If I look at the periodic table, this particular periodic table says 20.183. We're pretty close. We should be in the right neighborhood comparing it to the periodic table when we do this method properly. All right, let's take a look at another example. All right. Copper exists in nature as a mixture of 2 isotopes, copper 63, which is 69.17% of the copper, and copper 65, which is the rest. What is the average atomic mass of copper? Okay, this one's a little bit tricky because they didn't give us a second percentage value. We have to figure it out on our own. If 69.17% is the first isotope, 100 minus 69.17 is the rest, which would be 30.83%. So that's all that we have to do to figure out the abundance of copper 65. Now that we have it, 62.9296 AMUs multiplied by 69.17% to four significant figures is 4353 AMUs, 64.9278 AMUs times 30.83% is to four significant figures 2002 AMUs. I add those together and I get 6,355, which when I divide by 100 to get rid of the percent, 63.55 AMUs is the result. And that matches almost exactly to the periodic table on my desk here. All right, last problem, and this is probably the most challenging of the problems. Here is an example of another kind of problem that you could be asked with regard to percent abundance and isotopic mass. We know that silver has two isotopes, silver 107 and silver 109. The masses are there in the problem. We know that the average mass of silver is 107.87 AMUs. What is the natural abundance of each isotope? Now, this is tough because what we're essentially doing is we need to look at the problem differently. My average mass is equal to the mass of silver 107 times its abundance plus the mass of silver 109 multiplied by its abundance. Now we know what some of these values are. We can plug them in. 107.87 AMUs is equal to 106.90 AMUs multiplied by X, and 108.90 AMUs multiplied by Y. But you're looking at this and going, well, okay, I know my basic algebra 2 here. I've got two variables in one equation. How do I solve this problem? Well, again, you got to go back to your algebra 2 and realize that if you have two equations that both use the same two unknowns, you can use one equation to help solve for the other. Now, what is that one equation? Well, that one equation is the fact that X and Y have to equal 100%, which would be an abundance of 1. So rearranging that, I could get that X is equal to 1 minus Y. And if I substitute that in to this first equation, now I have a single variable that I can solve for. And once I know that variable, I can use it to figure out the other. So from that standpoint, 107.87 AMUs is equal to 106.90 AMUs minus 106.9 AMUs times Y plus 108.90 AMUs times Y. Also, combining like terms, I'm going to subtract the 106.9 from both sides. And I get 0.97 AMUs is equal to 2.000 AMUs times Y, dividing each side by 2. 0.97 divided by 2 gives me a value of Y to two significant figures of 0.49. 0.49 is 49%, which means that X is 1 minus 0.49, which is 0.51 or 51%. So because of the lack of precision in our values here, we cannot take it too much further than we did. But even if we did what the calculator had for us, 0.485 and 0.515 would be the answers there. So when you get a problem like this, where it's asking you to derive the natural abundance of each isotope, this is what you ultimately have to do. You have to set an equation that puts the two abundances as being somehow equal to each other, or at least an equational equality, and then substitute in and solve the problem. And so that concludes this particular lecture for today. When we come back, our next lecture will be another more calculation-focused one, where we start to look at the mole concept and how we count things in chemistry. Until then, take care and have a good day. I'll see you in lecture.